In this video, we'll look at some basic derivative rules. Here are the main points to be addressed in the video. The derivative of a constant function is 0 because constant functions have a rate of change of 0 at all input values in their domain. The power rule is derivative of x to the n power equals n times x to the n minus 1, where x is a variable and n is a number. A derivative of sum of monomials is the sum of the derivatives. The formula for differentiating an exponential function is d of dx of an equals a to the n power times natural log of a. The formula for differentiating a logarithmic function is derivative of log base a of x equals 1 over x times natural log of a. Derivative of sine x is cosine x, and derivative of cosine x is negative sine x. So first, let's look at power rule, which applies for constant and polynomial functions. A constant function is where the output of a function stays the same as input increases. For example, f of x equals 4 is a constant function. If you make a graph of f of x, it looks like this. The derivative of f of x equals the limit as delta x goes to 0 of the ratio of delta y to delta x. As x increases, y values do not change. So the derivative is 0 for all values of x. In general, if you have a constant function f of x equals c, then the derivative function is f prime of x equals 0. What if we have something a little more complicated? This is a type of function called monomial. A monomial function looks like some number times x raised to another number. The number that multiplies x is called a coefficient. The power that x is raised to is called an exponent. Coefficient and the exponent can be any number: whole number, fractions, negative numbers, or other numbers like pi or the square root of 2. Here's an example of a monomial. The coefficient is 1.7 and the exponent is 0.5. Note that both these coefficients and exponents are just numbers, not variables. The general rule for finding derivative of a monomial function is first, multiply the coefficient by the exponent, and then subtract 1 from the exponent. So in this example, we will have the new coefficient is 0.5 times 1.7, and the new exponent is 0.5 minus 1. Sometimes, things don't immediately look like the monomials. For example, here's a function that has x in the denominator. In this case, you need to rewrite this to see how it is a real monomial. Remember, an exponent in the denominator can be written as an exponent in the numerator multiplied by negative 1. And then you can apply the rule for monomials, the power rule. Multiply the coefficient by the exponent and subtract 1 from the exponent. A polynomial function consists of sum or difference of a bunch of monomials. Here's a generic polynomial function. The a, b, and c are coefficients, and the r, s, t are exponents. To find the derivative of a polynomial function, you find the derivative of each monomial using the power rule. You multiply the coefficient of each term by its exponent, and then subtract 1 from each exponent. Sometimes things don't initially look like polynomials, like this function that has radical signs and exponents that aren't just whole numbers. But you can use algebra to rewrite it. In this case, you can rewrite the radical sign as a fractional exponent. And then you can apply the power rule to each term in the function. multiply each coefficient by the exponent of that term, and then subtract 1 from the exponent. And also remember that derivative of constant is 0. Now let's look at more derivative, specifically exponential and logarithmic functions. An exponential function is where the output of function is a number raised to the value of input. For example, f of x 3 to the x is an exponential function. In contrast to a monomial, where the exponent is a number, an exponential function has a variable in the exponent, and the number is called base. Let's take a moment to think about what this will look like if you graphed it. Here are axes that we'll use to graph f of x and an approximation of its derivative. First, we'll show graph of f of x. Here's a graph of f of x. Next, let's think about what the graph of its derivative might look like. We'll start by picking a fixed delta x and look at how delta y and delta x changes together as we draw the graph of f of x. What we can observe is that for a fixed delta x, the ratio of delta y to delta x starts off close to 0 and then it gets larger and larger. Take a few moments to think about what the graph of this ratio will look like. Now let's draw a graph that approximates f prime of f of x. What you should notice here is that graph of f prime of x has the same basic shape as the graph of f of x. It turns out that if you have a general exponential function, f of x, a to the x power, then its derivative is natural log of a times a to the x power. So in the example here, the derivative is natural log 3 times 3 to the x. Keep in mind that ln 3 means natural log of 3, which is just a number. So the derivative of an exponential function, f of x, is a constant multiple of f of x. And that's why the graph of f prime of x had the same basic shape as the graph of f of x. Here are a few examples. At the top of the screen, I'll include the rule for finding derivative of an exponential function. Here are 4 examples. Take a minute to think about for each of these examples. We can use the rule for exponential functions. For f of x equals 7 to the x, you can see that the base is 7 and the exponent is just x. So we can use the rule and the derivative would be the natural log of the base times the original f of x. For f of x equals e to the x, you can see that the base is e, which represents a number, and the exponent is just x. So we can use the rule, and the derivative will be natural log of base times original f of x. You should remember that the natural log of e is just 1. So in this case, the derivative function gx is just e to the x. If you look at hx, it has a base of -3 and an exponent of x. But if you try to use the rule to find derivative of h of x, you run into trouble because the natural log of negative number is not a real number. So you cannot use the rule with h of x to find the derivative. If you look at j of x, the base is a positive number. However, the exponent is sine of x. And our rule only applies when the exponent is a variable, not another function. So it does not work here. So what if we have something a little simpler in the exponent, like 2x? At first, it looks like we're in the same situation as before because our rule for derivative of exponential function requires that we just have an x as an exponent. However, in some cases, we can use the properties of exponents to rewrite the equation. In this case, we can rewrite 7 to the 2x as 7 squared to the x. And now we have written j of x as base of 49 and an exponent of x. So we can apply the rule. Next, we'll look at derivative of logarithmic functions. Probably the most common log function you'll see is called natural log, which is written f of x equals ln of x. The derivative of f of x is 1 over x. One thing important to note is that you can only take log of positive numbers. So the domain of derivative is only positive values of x. There are also other types of logarithmic functions. For example, the 7 here is called base, and this function is log base 7 of x. You might remember some of the rules for rewriting logarithms. This one can be written as natural log of x divided by natural log of 7. And remember that natural log 7 is just some number. So we can rewrite this as 1 over natural log of 7 times natural log of x. And the derivative is 1 over natural log of 7 times 1 over x. And of course, there was nothing special about 7. So this gives us a general rule for derivative of logarithmic functions. In general, the derivative of log base a of x is 1 over natural log of a times 1 over x. Here are two examples. Take a minute to think about for each of these examples, and we can use rule for logarithmic functions. Like with power rule, you can take the derivative of two log functions that are added together. The base of the first one is 10. And the base of the second one is 2. So you will get 1 over natural log of 10 times 1 over x is a derivative of the first one, plus 1 over natural log of 2 times 1 over x is a derivative of the second one. Also, like with the power rule, you can multiply the derivative of the log base 10 of x by the coefficient. The base is 10 and the coefficient is 7 for g of x. So you will get 7 times 1 over natural log of 10 times 1 over x. Here are two more examples. Take a look at the input of h of x. The log rule only works when there is just an x for the function's input. It does not work if there is a sign inside of log. So we can't use the rule above to find the derivative of h of x. At first, it looks like j of x has same issues as h of x because input is not just x. But in this case, we can use properties of logarithm to rewrite the j of x. We can rewrite it as the log base of 10 of 2 plus the log base of 10 of x. Then we can find the derivative. Remember that log base 10 of 2 is just a constant number, so derivative is 0. And the derivative of log base 10 of x is 1 over natural log of 10 times 1 over x. So now we have seen a rule for computing derivatives of logarithm functions and some examples of how to use them. Lastly, let's look at trigonometry derivatives, specifically sine and cosine functions. We'll usually start thinking about sine as a ratio in a right triangle with the angle of interest having measure theta. Specifically, sine of theta is a ratio of the length of the side opposite theta to the length of the hypotenuse. To simplify things, we usually imagine that the triangle is embedded in a circle that has a radius 1, which makes the length of hypotenuse equals to 1. And so the sine theta is just equals to length of the side of the triangle that is opposite theta. Let's shrink this down so we can add coordinate axes and make a graph of the values of sine graph. Now let's add some coordinate axes. Now, the length of the side opposite the angle will be y coordinate of the point P. Let's increase the angle theta and graph the y values we get. This is a graph of function sine of theta. What would a graph of derivative of this function look like? Let's rewind this. And now let's zoom in a bit on the unit circle. Let's think about the derivative of sine of theta. We can approximate this value by looking at the ratio of the amount of change in sine of theta per amount of change in theta for very small values change in theta. And we should keep in mind that since the circle has radius 1, sine of theta is just the length of the side of triangle opposite theta. Let's think about the derivative when theta equals 0. Let's look at what happens when we start increase theta by a little amount. In particular, think about how the length of the opposite side of the triangle grows as in comparison to the measure of the angle. As theta increased, the length of the adjacent side, the blue line, did not change. So in a sense, all of the theta's increase went into opposite side of the triangle, the red line. This suggests that when theta was 0, the length of the red line increased the same amount as theta. This tells us that when theta equals 0, the derivative of sine is 1. Next, let's look at what happens when theta is close to pi over 2 radians. Since theta isn't close to 0, it's no longer the case that sine of theta is approximately the same value as theta. Now, let's look at what happens to the ratio of sine theta to theta as theta gets closer to pi over 2. As theta gets close to pi over 2 radians, the length of the opposite side of triangle, the value of sine theta, didn't really change. This tells us that the value of the derivative of sine of theta at pi over 2 radian is equal to 0. If we continue to look at how the value of sine changes as we go around the circle, we'll see that derivative of sine at theta equals pi will be negative 1. And the derivative of sine at theta equals 3 pi over 2 will be 0. Let's zoom back out. Let's plot some of the derivative values on our coordinate axes. Next, let's think about what values of derivative should be between these points. It turns out that these derivative values for sine of theta all matches the values of cosine of theta. So the derivative sine of theta is cosine of theta. Also, if you went back and examined how the length of adjacent side of the triangle changed in relation to theta, you could compute values for derivative of the cosine of theta. And you find that the derivative of cosine theta is -1 times the sine of theta.